Hi students. So very good morning everybody. So let us continue the chapter called alternating current, and we are about to finish the chapter. Let's start. What was the chapter we are discussing? Just a second. So the chapter we are discussing is alternating current, right? Almost the basics of the chapter we have done. So the first thing, so before, see, the aim of today's class is to learn about LCR circuit. What is this LCR circuit? Now listen, my dear students here. The first case what we have discussed is that there is a circuit in which a resistor of resistance R is connected, all right? So for this circuit or for this resistor, an alternating source is attached, right? In this case, what happened? Alternating EMF is E naught sine omega t, okay? And in this case, so the current we have got it as I is equal to I naught sine omega t. So is there any phase difference between E and I, right? So there's no phase difference between E and I. Okay, so both are in phase, my dear children. Both are in phase. And in this case, so this resistance is independent of the frequency. The resistance is independent of the frequency of this alternating source. Okay, and one more thing, and here, so V is equal to I into R. So this resistance, you can see it is equal to V by I only. It is independent of the frequency. After this, and one more point we had discussed in this case, what is that? The average power associated with this circuit is equal to I square RMS into R. Okay, so this is what the things we had discussed. Now the second case, let's look at the second case, my dear children. So the same, there is a circuit where an inductor is connected of inductance L, and which is connected to an alternating source here. Okay, and alternating source EMF E is equal to E naught sine omega t. Clear? So now when the current is passing through that, what we have got, your I is equal to I naught sine omega t minus pi by 2. So this is our current I value here. So there is a phi difference. So there's phase difference. So what is the phase difference we could identify here? It's pi by 2. Okay, and here resistance of this circuit is equal to, that is inductive reactance X suffix L, which is equal to omega is into L, which is 2 pi into frequency into L. See here, so this inductive reactance, which is the resistance of this circuit, is depending on the frequency of the oscillating source. All right, clear? Now, and one more thing, in this case, average power associated with this circuit for a complete cycle is 0. And let's draw the phasor diagrams also for your better understanding. So in the case of the first situation, so the phasor diagram, so let me draw here, so without any confusion. So this is the voltage and this is I. Okay, so phase angle is 0, both are in phase. In this case, so let me draw the phase diagram. So this is, for example, if it is I, and this will be V. Why? See here. So the voltage and this current is lagging. Okay, so current is lagging. Always current is lagging. I can say current is below the voltage. So this is voltage and this is current. So now third case, let us discuss. So what is the third situation, my dear children? So there is a capacitor which is connected to an alternating source. Capacitor whose capacitance is C. Okay. So in this case also E is equal to E naught sine omega t. Here when the source is on, so we get the current value I is equal to I naught sine omega t plus pi by 2. Here current is leading. Okay, so the phase difference identified was pi by 2, and here it is called capacitive reactance, which is the net resistance of this circuit. Okay, capacitive reactance is 1 by omega into C, which is 1 by omega is 2 pi into frequency into C. Okay, so here also you can see the capacitive reactance is depending on the frequency. Here, inductive reactance is directly proportional to frequency. Capacitive reactance is inversely proportional to the frequency. Okay, and here average power consumed in this circuit for a given 1 cycle is 0. So what is that? So is 0. And let us draw this event. So this is the phasor diagram. So if you say this is current and this will be the voltage, and you see here, so current is leading, yes or no, because we measure in anti-clockwise direction. So we measure in anti-clockwise direction. See, current is leading here and current is lagging here. Current is lagging, current is leading here. Okay, so this is the alternating current, the basic. So, and before that, what we have discussed, and before this, so we discussed about average current and RMS value of current. So just after learning average current and RMS value of current, we have done like this. When an alternating source is given to a resistor, when an alternating source is given to an inductor, when an alternating source is given to a capacitor, what happens to the current values? What happened to the phase difference? What happened to the resistance of the circuit? What will happen to the power? What will happen to the phasor diagram? See, so many things involved in this small talk. It is a quick recap. Okay. Now let us start. Before moving, just let me take this here for some time. Okay. So what is the topic? Is LCR circuit, my dear students. What is the topic? LCR circuit. You know how much importance is there for this? So you can expect a question for your NEET exam also in this LCR circuit. Commonly asked question is available from this LCR circuit. What is LCR? Here there is only resistor is connected in the circuit. Here there is only inductor. Here there is only capacitor. But now we are going to join all three of them in series. Okay. So let's have a look at this. So there is L. Okay. So there is capacitance. Carefully see. There is resistance. All right. So this is the circuit, and an alternating source is connected to this. This is the alternating source is connected to this. And here the EMF remains same. E is equal to E naught sine omega t. What happened to its current value? Let us check, right? So this is the inductance L. This is capacitance C. This is the resistance R. Okay. Now the source is connected. So when the source is on, what happens? So current I is passing through that, and 100% the same current will be passing through the three elements here. So what is that? What I can write? So same current will be flowing through all these elements because they are connected in series combination, my dear students. So here, if you really understand, so the potential across this is VL, potential across this is VC, potential across this is VR. So let us write one by one as the same current, okay, as the same current. So potential across this VL, what is that VL? So VL is equal to I into XL, okay. And from here, so VC is equal to what? I into XC, and VR is equal to what? I into XL. Sorry, I into XR. So this I into XR, I can write it as I into R. Okay. So remember these three. Right? So there is net potential difference you need to identify, and net potential difference of the net EMF you need to identify, as well as net current also we need to find. Right? So the aim in this concept is, let me write here, right? So let's take one more. So the aim of LCR circuit, what we are taking is number one. So let us find out net voltage of the circuit, net voltage of the circuit, and net resistance of the circuit. And net resistance of the circuit is also called as impedance, my dear students. What is that? Impedance, which is denoted with the symbol Z. So what is the net resistance and the net voltage of the circuit at T? I told you already, net resistance is named as impedance. Okay. So all right. So before that, I can directly write it as what is the total current passing through this I. I is equal to, so total voltage of the circuit E, and total resistance is impedance, right? So this is the final answer what we are going to get. Okay, I is equal to E by Z. All right, and let's start. Let's begin the topic now. Here, this complete concept we are going to derive and learn by using the phasor diagrams. By using what? A phasor diagram. By using a simple phasor diagram, we are going to understand this topic. Simple phasor diagram. What is that simple phasor diagram? So let us see. First thing, what I am drawing here is this one. So this is VR. Okay. So VR is what? Potential across the resistance, and the current and resistance are in the same direction in case of resistive circuit. In case of resistive circuit, in phasor diagram, see this, have a look at here. In case of resistive circuit, potential or the voltage and current are in the same direction in phase. All right. Now, this is the current will be lagging in case of inductive circuit. Look at here, inductive circuit. This is the inductive circuit. So this is lagging, my dear students. So current is lagging. So what is this? You know, this is VL. So here see, current is lagging by pi by 2. And one more. In this case, what happens? Voltage is lagging. Okay, that means current is leading. So current is here. So voltage is lagging. So this is what? V suffix C. This is called voltage across the capacitor, voltage across the inductor, voltage across the resistor. So this is the concept. So here also there is pi by 2 angle. Right? Now, let's understand the important topic here. Imagine this is the case. I am imagining that. See, I am assuming this is the case as VL is greater than VC. So that means inductor dominate circuit, right? So inductive dominated circuit. So I'm just imagining like that. Okay, inductive dominated circuit, I'm just assuming. So in this case, what happens? VL is here, VC is here. Which is greater? VL is greater than VC. If you consider this is the vector and this is the vector, so what happened to the net vector here, right? So net vector will be lying in the direction of VL. Okay. So this is the direction of VL minus VC. Okay, so that's the direction of VL minus VC. All right. So this is VR. So now there are two vectors. VR, we can imagine that is a vector. VL minus VC, that is imagine that can be another vector. So VR and VL minus VC. And these two vectors are at an angle 90 degrees, and you can find the resultant vector now. So that is the resultant EMF of the circuit, of this LCR circuit. So what is the resultant EMF, my dear children, here? So resultant EMF you can find out, see here. So you can make a triangle. So this is what VR and this is what VL minus VC. So finally I can write your E value is equal to square root of VR square plus VL minus VC whole square. Okay. Clear? So this is the net EMF of the circuit or net voltage of the circuit. Try to understand and remember this part. Now from here, what I can write? Carefully see. E is equal to, so here VR, I can write it as IR whole square plus VL. So VL I can also write it as I into XL minus I into XC whole square. So from here, I can also take common I square inside. When it comes to the outside, it will be I square root R square plus XL minus XC whole square. Okay, so from here, so what I can write? So E by I is equal to, E by I is equal to Z. So that is what E by I is equal to resistance. So what is the Z value here? Which is square root R square plus XL minus XC whole square. Okay. This is the impedance of the circuit. What is this called? Impedance of the circuit. And I is equal to E by Z. So E is what? That is E by Z is square root R square plus XL minus XC whole square. So this is the current passing through LCR circuit. This is current passing through LCR circuit. Okay. And this is the net potential across the LCR, net potential across LCR, right? And there is an angle here, so that's called phi. What is this? This phi angle. Phi is the phase difference between E and I. E is what? Net EMF of this LCR circuit, and I is the current. So for that, I can write I is equal to I naught sine omega t minus phi. You can see here, current is lagging. See here, this is current, this is current, this is current, this is current. Okay, and this is net EMF. So current is lagging by what angle? By phi. So this is the current in LCR circuit. Okay, clear? And in LCR circuit, what is the source voltage we provided is E naught sine omega t minus phi. No confusion. Sorry. E naught sine omega t. You can see here the phase difference is phi, and that is this phi. Right? Now, and one more thing from this triangle, and let's take this triangle here. So this is the triangle. It's so simple triangle here. This triangle is called impedance triangle. What is it called? Impedance triangle. So this is VR. Okay, so this is VR, just adjacent side. Opposite side is VL minus VC, and this is E. Okay. So now from this triangle, I can write tan phi. Tan phi value is how much? VL minus VC divided by VR. So the same can also be written as XL minus XC divided by R, because in terms of resistances we have discussed, in terms of resistances we have written. Okay. Fine. So alright, my dear students, in case of resistances we have discussed. So this is the most important triangle here. All right. So in this case, you can also write this opposite side is XL minus XC, and this is R, and this is Z. Okay. Clear, resistance of this is XL minus XC, and this is Z, and this is R. Because I is taken common in the numerator, and denominator also I is taken common. So tan phi can be written as like this, and from here I can write cos phi. Cos phi. What is cos phi from this triangle? Cos phi is equal to R cos phi is what? So cos phi is just the adjacent side by hypotenuse. Adjacent side by hypotenuse. Remember, cos phi is R by Z. R by Z. And this cos phi is called as power factor. What is it called? Power factor. Power factor. Now, one important thing I'd like to inform here. So there is here. So average power in LCR circuit will be equal to ERMS into IRMS into cos phi. ERMS into IRMS into cos phi. So this is the average power concept, my dear children. It is so simple. Just try to understand the formula here, and this here, this value here. Okay. Now, what we have got. Let me take the another page. Another page. Right here, what we have got. So this is VR or I. So this is VL actually, and this is VC. If it is capacitive dominated circuit, it is VL minus VC, and you have your final net EMF or net voltage across the LCR circuit is this one, right? Clear? Now, carefully see here, if this is the inductive dominated circuit, we have got I value is equal to I naught sine omega t minus phi, right? And tan phi, what is the value we have got? Tan phi from here. So tan phi is opposite side by adjacent side. Opposite side is what? VL minus VC by VR, which can also be written as XL minus XC by R. Okay. So, for example, this is the case when VL is greater than VC. Okay. R XL is greater than XC. So this is the condition, my dear students. Here, current is lagging only. As it is inductive dominated, in inductive dominated circuit, what happens? Generally, when an AC source is connected to inductor, what happens? So when AC source is connected to inductor, I'll just revise what happens in this case. You've got I is equal to I naught sine omega t minus pi by 2. Yes or no? Here also current is lagging. Here also current is lagging. When you take inductive dominated circuit, current will be lagging the EMF, right? So now let's take this one. So here, same things I'm taking. So this is VR and this is I. Same. So this is VL and this is VC. So let us take capacitive dominated circuit. So that is VC is greater than VL or XC is greater than XL. This is called capacitive dominated circuit. So here what happened? So this will be the final resultant vector VC minus VL. So in this case, you can see this is the net potential across the complete LCR. So this is your phi value. So you know what happened? Current is leading. Current is leading. Yes or no? So in this case, you get the current value I naught sine omega t plus phi. Current is leading the final EMF. Current is leading because we measure in anti-clockwise direction. No confusions, my dear children. Okay. All right. So in this case, what happens to tan phi? Tan phi is equal to always whatever it may be. Tan phi is opposite side by adjacent. So opposite side is VC minus VL by VR. So this can also be written like a numerator and denominator. You can take common. I you can take common and you get it as XC minus XL divided by VP. Only it's R because we are talking about resistances. It's R, right? Now, here there is a power factor and here also there is a power factor. And the most important thing, so this is called the capacitive dominant circuit. What is this? Capacitive dominant circuit, and the above one is inductor dominant circuit, right? So inductor dominant circuit. Now, one more. One more here. Same. VR, it's I. This is your VL. This is your VC. For example, VL is equal to VC. So that means your XL is equal to XC. Okay. So in this case, what happened? So the resultant of these two will be 0. And finally, you get your EMF this only. Your EMF is in the direction of VR. And this is called the pure resistive circuit. What is this? Pure resistive circuit. In case of pure resistive circuit, so phi value will be 0. So I is equal to I naught sine omega t. There is no phase difference here. So E is equal to E naught sine omega t. When VL is equal to VC or XL is equal to SC, VL means what? Potential across the inductor. VC is what? Potential across the capacitor. If these two are equal, so the circuit is becoming pure resistive. Remember, circuit is becoming pure resistive. Okay, clear. And when XL is equal to XC, so also the XL is what? Resistance, inductive reactance is equal to capacitive reactance, and we get circuit is pure resistive. Circuit is pure resistive. Okay, so no confusions, my dear children, here. Now, let me remove this so that we get some space. So let's concentrate on R value here. Net resistance is what? Impedance. Understand? So this is net resistance of the LCR circuit is called impedance. So that is R square plus what we have got? XC minus XL whole square. If it is capacitive dominant, if it is inductive dominant, XL minus XC. So whatever it may be. So that may be that here our assumption is XC is greater than XL, because if you take this is 100, this must be less than 100, otherwise negative value we get it. Understand? So now here let's take XC is equal to XL. For example, XC is equal to XL. What happens here? XC is what? XC is what here? XC is 1 by omega c, which is equal to omega into L. So this I can write it as omega square is equal to 1 by LC. So this I can also write it as 4 pi into frequency square. Okay, omega square is equal to 1 by LC. So which is 1 by LC, 4 pi square. Sorry. So from here, so frequency square is equal to 1 by 4 pi square into LC. So finally I can write frequency, you get it as 1 by 2 pi root LC. So very important formula I have got. So at this frequency, what happens, at this frequency, so the circuit will become, see, X is equal to XL. So VL is equal to VC. At this frequency, circuit will be having a pure resistive circuit. So this complete circuit will behave as, this complete circuit will behave as if it is only connected to a resistor. That's it, right? Just it is connected to resistor when, if this frequency, and this is the frequency is called resonance frequency. What is this frequency is called? Resonance frequency. At this frequency only LCR circuit will become a pure resistive circuit. And let's substitute this. Let us see an important thing. So this X is equal to XL, you substitute this. So what happens? Let us check here. So what is that? Z is equal to square root R square plus XC minus XL, or XL minus XC. Both are same, right? It is 0 square. So what is that? Z is equal to R. Z is equal to R. When Z is equal to 1. So the complete impedance of the LCR circuit. What is this Z? Again I am writing you. It's complete impedance of LCR circuit. Complete impedance of LCR circuit become just a resistance. Right? So that's the important point here. Now, this is what the topic called LCR circuit, and there are so many numericals are available based on LCR circuit. And before going to the so many numericals, let us have a discussion based on a simple numerical. So I have a numerical with me. So look at here, there is L, there is a resistance, so there is a capacitance is connected here. This is connected to an alternating source. This alternating source voltage and frequency is also mentioned. So frequency voltage is 220 volt and 50 hertz is mentioned here. And this L value, this resistance is given. XL is equal to 100 ohm. Okay. So this is resistance is given as 60 ohm. So this resistance XC is given as 20 ohm. You know what is the question? So question is, what is the power factor? What is the power factor? So question is, find the power factor, my dear students, right? Power factor. So what is the power factor? So we had already discussed power factor topic just now. So power factor topic we discussed. What is the power factor? Power factor is simply cos phi. So to find this power factor, you should know the impedance triangle. So impedance triangle, draw the impedance triangle. If it is phi, so this is R, right? Resistance we are talking, all the resistances are given, you can see. So resistance, resistance, resistance. So this is new, this one opposite side of this is XL minus XC. Understand? XL minus XC. Yes or no? Because of what? It is XL is 100, XC is 20. It is inductive dominant circuit. Okay, and this is what? So this is the Z. So net resistance Z impedance. Okay, so what we need to find the cos phi value is how much, my dear students? From this cos phi value is equal to adjacent side by hypotenuse, right? So R by Z. R is what? Resistance of the resistor. So this is 60 divided by Z. Impedance is Z. That Z if you find, and you get this power factor. So what is Z? So we have the formula for Z. Z is equal to R square plus here XL minus XC whole square. Okay. Z is equal to square root R square. What is R square here? It is 60 square plus XC minus, sorry, XL minus XC. 120. So 100 minus 20, it is 80 square, my dear students. So Z is equal to, it is 3600 plus 6400. So what I can write here, it is root 10,000. So it's equal to 100 ohm, my dear students. What is that? 100 ohm. So finally, our concept is power factor, which is equal to cos phi, which is equal to R by Z, 60 by 100. 0, 0 cancel, right? So the power factor is equal to, so it's 3 by 5, my dear students. So like this, the questions will be asked. All right, clear? So here two questions we have solved. So one is Z, finding the Z. Finding Z in Z is the net resistance of the circuit, net opposition of the circuit. Okay. Let's see the another question. Simple basic question I'll tell you. Simple basic question I'll give you. There is a circuit, alternating current is connected. So resistance. So there is a circuit. Now a capacitor is also included. Resistor and capacitor. So question is, what happened to the current? Initial current and the final current, right? So in this case, see, we know current value will increase when impedance will decrease. Simple. Okay, remember this. So here, what happens? Impedance, let us calculate. Impedance is the resistance only this value, right? So in this case, what happens is Z is equal to square root R square plus here XC minus XL whole square. Carefully see, XC minus XL whole square. Here, previously there is no XC XL. So Z is equal to R. In the first case, what is that? Simple. Z is equal to R. So in this case, what happened in the second case? So Z is equal to square root R square plus this is XC square. So Z value increased or decreased? Carefully see, my dear students. So initially Z is equal to just R, right? So just R. Now Z value is increased. Understand? When Z value is increased, so definitely current value will be decreases. Current value will be decreases. Understand? Clear? Like this, the questions will be asked. Are you ready? Are you ready to solve one more question? And let's solve one more question. Let's have a look at the another example, my dear students. So look at the another example. Just have a look at this example here. When a coil, right? When a coil, I'm just writing the question. When a coil is connected, when a coil is connected to a 100-volt DC supply, the current is 2 ampere. When the same coil, when the same coil is connected to an AC source, AC source voltage is equal to 100 root 2 sine omega t. In this case, so the current they identified is 1 ampere, my dear students. Now the question is, find the inductive reactance. Find what? Inductive reactance in the circuit. Right? What is that? Finding the inductive reactance in the circuit. So it's so simple here. So let's read the question step by step. All right. So let us read the question step by step. So what is the question given? When a coil is connected to a 100-volt DC supply, the current is 2 ampere. So the coil means an inductor. Okay. When there is an inductor, definitely there is a resistance associated with this. Okay. So we have I is equal to V by R, and from here R is equal to V by I. So what is this? 100 by current is 2. So I can say the resistance of the coil is 50 ohm. What is the resistance of the coil? 50 ohm. Now, when the same coil is connected to an AC source, 100 root 2 into sine omega t, the current is 1 ampere. Now the current is 1 ampere, and when it is connected to AC source, the current is called IRMS. Yes or no? When it is connected to AC source, the current is IRMS, which is equal to ERMS divided by, I'm talking about when it is connected to AC source. So here, when it is connected to AC source, there is a coil, and the coil will have some resistance, and the AC source, it is connected like this. In this case, current is IRMS. So ERMS is the value of the at any instant value of EMF, and resistance is the impedance here. Understand? Because I'm talking about the complete circuit. So resistance is impedance. All right. So the question is to find. What is the question? Question is to find inductive reactance. Inductive reactance is X suffix L. That is the question. So here IRMS value is given as 1, which is equal, see here, IRMS is 1, which is equal to ERMS. E naught is 100 root 2, and ERMS, we know ERMS is equal to E naught by root 2. E naught is 100 root 2. 100 root 2 by root 2 is 100. So E naught is 100 divided by Z. So what is the Z value here? So Z into 1 is equal to 100 ohm. Okay, so our aim is to find what? XL. So let's use the formula. Z is equal to R square plus XL minus XC whole square. Interesting thing I'll tell you. This is the circuit is called LR circuit. No, there's no C. Sometimes the question may be based on CR circuit. There's no L. In that case, this L need to be cancelled. In somewhere the question may be LC circuit, no resistance. So this will not be here. Understand? So our circuit is LR and there's no C here. So Z is equal to square root R square plus XL square. Just substitute everything. Everything you have, resistance you have, Z you have, XL you can find out from here. I can also write your Z square is equal to R square plus XL square, my dear students. So Z square, okay, XL square I need to find out, which is equal to Z square minus R square. So Z square is 100 square minus r square is 50 square. Okay, so from here you can get xl is equal to 50 into root 3. Oh, what is the SI unit of resistance? Ohm. Okay, clear? So that's it. And there is a continuation of LCR circuit, some more numericals, right? Continuation of LCR circuit, some more numericals, and LC oscillations. Depends on the time. LC oscillations. This is our next topic, my dear students. Right? So all the very best for your assignment and your future.